So we will continue the lectures from previous week. Uh, Last week we talked about the basic flow theory for the hydrostatic bearing. Most of them who calculated the flow rate or witness pressure for the different bearing shape and different restrictor. So So we have to write some of the equations for the circular bearing passing through the capillary restrictor, blood restrictor, and as well as the orifice restrictor. Okay, so it's mainly the two-dimensional Rayleigh equation to derive the volume flow rate for certain bearing shape and certain restrictor type. Okay, so we have some volume flow rate and mass flow rate, and also the reset pressure. Okay, the reset pressure for the bearing. So today we will continue for this section 2.8. Maybe you can go back a little bit from chapter 1. In the chapter 1, this is the circular bearing. It's a thrust bearing for axial load. So here is the restrictor. So from the pressure supply system, you have a supply pressure to the hydrostatic bearing system. So the supply pressure is the PA. Okay, and we install the restrictor on the upstream of the flow line. So we have a restrictor here. No matter what kind of a restrictor you pick up. In this case, we have a repeat restrictor here. Okay, so for, for the restrictor, the function mainly to regulate or to adjust the pressure, to change the pressure to supply pressure PS into the recess pressure. So usually we call the recess pressure PR. Okay? So the function of the restrictor is to regulate or to adjust the pressure from PS to PR. PR. So now in this section 2.8, we want to calculate the recess because it's important for the bearing design, because of the bearing design, we care about the low capacity for the bearing we can carry. This is the low capacity. Usually it's equal to the recess pressure multiplied by the effective or equivalent area of the bearing. This is the low capacity. Low carrying capacity. So we want to calculate the load for the bearing that can carry using these formulas. So the next step, we want to calculate the recess pressure. The pressure right after the restrictor. Okay. So in this case, let me look at the 2.8 or chapter 2 in page 37. So this this recess pressure can be calculated from the equation. We call it continuity equation in the beginning. So mass flow rate passing through the restrictor will equal to the mass flow rate flow out by the bearing. Okay? So which means that the volume flow rate or mass flow rate passing through the restrictor must be equal to the mass flow rate get out of the bearing. By using this equation, you can so this is the volume flow rate get out of the bearing. This is for this for the circular bearing. Okay. So in this case, you can extend the PR. I think it's two 225 or 224. Yeah. This is the equation for the PR. Okay. So this kind of a formula is related to different flow restriction. In this case, for the laminar flow restrictor like capillary, you can obtain this for this form of the formula for the hydrostatic value. Okay, so this is the V bar and this is the PhD because for this one it's a simple form for the formula instead of getting complicated formula like page 37. You can look at that in the textbook as well. Here is the formula you can obtain for the capillary restrictor circular bearing test. So you can obtain this PR equal to this one. So this is for the capillary restrictor. But it's a bit difficult to observe for this one. So you can use this one. Okay, by using a simple notation for B line DC. Okay. So this C, the kernel of C is related to the capillary chemistry. And for the aerostatic bearing or air bearing, we have this it's a more complicated form for the PR. You can obtain for the air bearing. The air bearing, you can have this PR. So PS is the supply pressure, PA is the gauge pressure for the estimate here. Okay. And R2 is the outer diameter for the circular bearing. R1 is the inner diameter for the circular bearing. You can have a look at from previous chapter 1. Okay. So this one is R2 and this one is R1. Right. be discussed in chapter 3, next chapter, to discuss for different bearing shape, how you can calculate that is equivalent bearing area, so that you can calculate the load capacity for the bearing shape. So, but in this chapter 2, we were dealing with the research question. So here we could derive some of the formulas for PR with a different restrictor. In this case, it's the capillary restrictor. So next one we will calculate the PR for the blood restrictor. Or if you choose your bearing pad design with the orifice restrictor, you can also calculate the PR for the orifice restrictor. Okay. But later we will discuss why you can choose a different restrictor for the design. For the large hydrostatic rotary table, like we discussed for the vertical turning machine, so it's very large turning table, and it's very heavy loading. In that case, usually you need to choose your restricted design with capillary, because of capillary restricted design, usually it's not sensitive to the temperature rise. Okay. But however, in the smaller spindle design, usually we would choose the orifice restrictor. Okay. So normally for the heavy loading machine or heavy loading rotary table, hydrostatic rotary table, we choose the restrictor of the capillary design. For small spindle, it's difficult to install the capillary tube. Then we will choose orifice restrictor instead. So in this case, from the formula, this is quite important, the conclusion in this page. So this PR, in this relationship, we don't have any viscosity inside the formula. Okay. So vocabulary restricted design is not sensitive to the temperature rise. 毛细管节流器的话，就是它这个公式里面是没有粘度的油的粘度在里面，所以毛细管的节流器的话，通常都是对温度比较不敏感，所以负载如果非常重的话，通常我们都会去选节流器是毛细管，因为你的负载非常重，你压下去，你的油膜的厚度其实会变得很那如果是转起来，尤其是大型旋转工作台、大力车，它其实温升会很严重。其实它的温度变化、温升会很高，温度变化很大。如果你选那个小孔节流器的话，它其实是对温度很敏感。毛细管节流器，你看在公式里面，you don't have any lubricant form in this formula. So that's why the resistance pressure for the capillary restrictor is independent of the viscosity. So in this case, for capillary restrictor design or capillary controlled hydrostatic bearing, are prone to insensitive to the change of the temperature for the lubricant. Okay? So this is quite important. So in the next, we will write the relationship for the for the recess pressure of orifice restrictor design hydrostatic bearing. So in this case, for hydrostatic bearing, you see the data here. This is lubricant. No, this is the viscosity of the lubricant form here. So we know when the temperature rises, the viscosity of the lubricant will drop dramatically. So in that case, the temperature difference for your lubricant will affect the research pressure. So in this formula, you see the viscosity form for your lubricant here. Okay. So this is the research pressure for the circular bearing on the hydrostatic bearing. So the anode here is the restriction area for the orifice restrictor. Again, you can look at the some of the notation of previous one. Okay, so here is the anode here for the restriction area for the orifice restrictor. Last week we also talked about the orifice restrictor, the discharge coefficient CB will be different if you have a different design of the orifice. And usually this one should be tested by experiment to get exact values for your design. But usually we can have a guessing for this CD. Okay, it's around zero point 0.5 to zero point 0.7 or zero point 0.6 to zero point 0.7 in the range of point 0.5 to point 0.7. Okay. So for the orifice restrictor design hydrostatic bearing, the resistance pressure depends on the viscosity. Okay. So when your system warm up due to the viscous, due to your lubricant friction between the viscous fluid, you will have temperature rise in your lubricant, and usually the viscosity will drop in that case. Okay? So when temperature is rising and the viscosity is reduced, so this will cause the bearing film thickness will drop. Right? Okay. So for Olympus restrictor, it is important you have a cooling system for your pressure supply system to control or to, or say, to fix your lubricant temperature under certain range of the temperature. Okay. You don't have such a freedom like a capillary design or slot control. This, these two are the laminar flow restrictor. So they are sensitive to the viscosity change or sensitive to temperature. So this is the equation for the PR, for the hydrostatic bearing, for the, no, no, this should be wrong. This one should be, what? 125. Yeah. So this one is laminar flow. This one is, so this is actually the formula in page 37, equation 2.25a. Maybe this one is 2.26. Okay, this is orifice, and this is the capillary restriction. And we have another definition for that. It's called the pressure ratio. Okay. Pressure ratio is the resistance pressure divided by the supply pressure. So the beta is called the pressure ratio. So this is in page 39, page 39. And for the gases, we have gauge pressure ratio for the air bearing. Yeah. Especially for the air bearing. This gauge pressure is usually also called flyover pressure. So it's the atmosphere larger than the calculation for usually in the design. So next, in page 29 for the very loading, okay, we have in previous chapter, we have two different designs. This is the circular bearing design, one for hydrostatic bearing, one for the aerostatic bearing. And these two are for the slot orifice, slot restrictor design. So and usually you can ignore this one because in practical application, none of the commercial product design with the slot restrictor. 所以在实际商业应用来讲，狭缝节流器的产品不存在。狭缝节流器制造起来比较困难，而且不容易控制它那个油这些的回收，所以基本上商业产品的话，大概就是两种，固定节流器就是毛细管节流器跟小孔节流器。对，so 小孔节流器就是这个 orifice restrictor。毛细管节流器的话，就是 capillary restrictor。所以大部分的传统的商业产品大概就是毛细管跟小孔设计。其实还有那个我们后面会讲那个薄膜节流器。薄膜节流器的话就是 so for traditional hydrostatic bearing, usually the commercial product was designed by the capillary restrictor or the orifice restrictor. And so for the slot restrictor, never exists in the commercial product. Okay, so forget about it. But because we are in the lecture of the graduate school, we need to discuss the theoretical background. But it's useless in practical application. Right. Okay. So here is the circular bearing. Okay. So this is for hydrostatic bearing, and this is for the air bearing. Okay. And then the final goal is that we need to estimate or predict or calculate the bearing load capacity in your design stage. And here is the formula. You can calculate the circular bearing capacity. Okay. So actually, the same equation I write before, I wrote before. So the load capacity, very low capacity equal to the recess pressure multiplied by the equivalent of effective bearing mass area. So, and we will come back this how to calculate the equivalent bearing mass area later in next chapter. Okay. But in this chapter 2, we only discuss the simplest one, the circular bearing. 所以不同的轴承的构型，我们要去计算它有效的那个轴承面积，油浆的面积。 们这个下一章会介绍，但这边我们通通都是用呃圆形平面轴承来介绍这些理论。So this is for the circular bearing height, okay? And on the horizontal is the R divided by R1. Okay? R1 is this is the recess, bearing recess. Here is the radius of the recess R1. R2 is the outer radius of the circular bearing. R is radius in any position. Okay, you can estimate this. And here is the supply pressure divided by the research pressure. Here we have a kind of a drawing for that. For the air bearing, if you have a recess, usually it will be flexible. If the supply pressure is greater than 6 bar for the air bearing, and for the hydrostatic bearing, if your supply pressure is higher than 60, 65 or 60, you will be convectible. If it's lower than 60, the lubricant you usually is considered convectible. Okay? So it follows this curve. So that's why when you design your air barrier, it's necessary to consider the stability for your air barrier. For the recess design, in considering the design of your recess, you always need to consider the stability for the air element stability. And this is the other design for the most of the machine tool applications have a close opposite truss bearing. So in this case, we can have this is a slide table, or this is a fixed rail. You can have a whole structure here with another, I would say, symmetric drawing like this. So this is the fixed rail, and this is the opposite blend transparent. And usually we design because we need to have some loading on the table. So the loading may include the, the weight of the long piece and also the cutting force in the vertical direction. So in that case, we need to design the bearing at for the bottom side bigger than the top one. So the area KE2 usually is bigger than the AE1. So that you can handle normal loading, extra loading. So在做封闭型的这个 工作台的设计的时候，通常下游腔要比上游腔大，因为我们有上面的负载在上面。对，we'll connect this to this later when we basic the practical design of the hydrostatic bearing. So again, we have this kind of morphology for the pressure set bearing or external pressurized hydrostatic bearing. So you have a different bearing types. The first one is the aerostatic bearing. Second one is hydrostatic bearing. And we have another one called the hydrodynamic bearing. Okay. And we have, if you are rotating at very high speed, you will have a hydrodynamic effect. So in that case, you will have a hybrid bearing design. But usually, you need to rotate very high speed. I would say more than 10,000 RPM. Okay. From theoretical point of view, we have made some estimations for that. For the rotational speed for the spindle, if the rotational speed RPM is smaller than 30,000 RPM, the influence is only 3 to 5%. Okay? So we expect if you have a rotational speed greater than 100,000 RPM, you will have a significant improvement for your low capacity display for hybrid bearing design. So to understand it, usually in a machine tool application, when you design your air bearing spindle, you are running at very high speed, let's say 10,000 RPM. You don't need to consider. If you are running 100,000 RPM, then you need to consider hybrid bearing design. Or you need to consider hydrodynamic effect for your full film bearing. But I would say the influence is still limited. I think for 10,000 or for 100,000 RPM, the effect only 5 to 6% increase in your stiffness and load. So usually in machine tool application, no matter you are hydrostatic bearing or aerostatic bearing, if you are running in relatively low rotational speed, I would say less than 100,000 RPM, you don't need to consider the hydrodynamic effect. 就是在通常来讲，就是流体在高转速的时候，它其实会有动压的效果造成，因为你的流体流动的压力会造成让你的那个负载跟刚性增加。那在我们的经验里面，就是如果是10万转以下，基本上是完全不用考虑动压的效应。所以我们一般设计都还是把它当成静压轴的设计，完全不需要考虑，因为大部分 because most of the applications for the machine tool for hydrostatic bearing or aerostatic bearing, okay, the rotational speed usually in lower than 100,000 RPM. Okay. So in that case, you don't need to consider the hydrodynamic effect. 所以大部分的在工具机用的，不管 静压、低静压或低静压的品种，都是10万转以下，所以基本上动压是完全不需要考虑，因为我们其实从理论上计算过，就是你转到5万转的话，它的影响对你整体刚性的影响的话，就是增加3到5%。所以你用静压轴设计的话，你有动压效应，只是让你的承载跟刚性会更大，所以只是会你的轴承会更好，不会更糟糕。Okay. So we take a break for now. So for the hydrostatic or aerostatic variance, you can only consider the hydrostatic variance. You don't need to consider the hybrid variance sign in most of the cases. Okay? So this is the journal variance. Last week we talked about the diameter, diameter, inner diameter here, length is the variance. So usually we design the journal variance with diameter equal to the length. This is for the normal. For heavy loading, usually not so big, 1.2 or 1.3. Okay. If for the lightweight design, so if for the regular or normal bearing design, we always design the joint bearing with the diameter divided by the length equal to 1. Okay. So for heavy loading, you can have a diameter. a four recess journal bearing design. Okay, we have four recess journal bearing. So later in I think in chapter 3 or chapter 4, we will tell you this A must equal to the quarter of the error. Okay? This is the rule of thumb to design the journal bearing. 就是我们一般习惯设计，就是我们怎么去取舍这个风油边的长度，通常都是取1/4的。所以如果没有特别的说明，我们的这个内径这个 D 跟我的这个长度是一样，大概是这样。So this is the vertical direction and the horizontal direction for the journal bearing. So the original book is incorrect. So to correct it, so this one should be cosine. Instead of the sine, it should be cosine. Okay. This is also cosine. 原本书上是有错误，there are some mistakes in the original book. Okay. Right. So this is in the chapter, no, in the page 42. And next, normally in the fluid dynamics or fluid mechanics, we like to use normalized data, which means the result of the discussed here can be used, can be applied universally if the form or the configuration of the bearing are similar. They can use the result, okay? Not just its specific dimensions are valid. 所以我们这边会去介绍叫做正规化，或者是叫做正常化，也有人叫做无因式化。通常流体力学就会去推导一些无因式的公式，因为我们流体力学很多都是做实验去验证，它都是有特定的尺寸在这个实验里面。那如果我们要拿推广这个结果，可以用在不同的尺寸，但只要它的构型是类似，所以通常我们都把它的式子推导成无因式方式。 some normalized data. So the use of normalized data writes the principle for this specific case can be applied the other dimensions universally. So usually we use normalized formula to analyze the problem. Okay. 所以我们这边就会有一些无因制的一些数据，就像我们这边负载的话，其实会等于油枪压力乘上我的油枪的面积，再乘上我的面积的因子一把。Okay. So we have here the equation for the low capacity equal to the recess pressure multiplied by net area, bearing net area, and multiplied by the area factor in bar. So here we have a table here. We also have another normalized or dimensionless form as a low capacity. Okay, is equal to the divided by the PS multiplied by A. So the here we have a dimension group that normalized. So 我们就是要把它的那个单位除掉，把它变成是无因式的形式。面积的话，我们就除以一个总面积，除下来的话，它们就是一个面积的无因式。So we have a table. So talk about the pressure ratio. Resistance ratio divided by the supply pressure. So for this pressure ratio is normalized parameter. And we also have an effective area. If we normalize this term with the total area, overall area divided by A, so this one is normalized effective area. Okay, so you don't have any dimension. Usually for area, we have a unit of meter square, millimeter square. But in this case, its dimension as one. For the low capacity is the same. For low capacity, we divide it by the PS multiplied by the equivalent very thin area. And later on, we will discuss about this flow shape factor for the hydrostatic bearing, flow shape factor for the area, and flow pressure factor, and speed parameter for the Joule bearing, speed parameter for the truss bearing, and film thickness. Okay. In this case, film thickness. So this one is dimensionless one. It's a normalized data. Then the result of your experiment can be used in nursery. The configuration is similar. 所以他用这个无因式或者是叫正规化的数据的话，其实就是要让我们这个实验出来的结果，让它的样式或形式是轴承的形式是跟我们这个发表的这个推导的这个结果是类似的，都可以应用在上面。所以它就表示我这个公式其实是跟尺寸有关。So this one is the page 43. Okay. So the applied pressure. So this is the local density equal to the PA multiplied by AD multiplied by normalized flow capacity. E. Okay. This is an example for the 2.1. Right. And then the aerostatic value. Okay, aerostatic value. For this textbook, they give you only the result. There's no variation for the formula. Only give you the final result. But you still need to read the text carefully. Okay. For most of the aerostatic value in practical application, usually they use the orifice restrictor. Most of the case. 所以大部分的气压轴承在实际应用上都是使用小孔节流器或空口节流器。Only very few use capillary restrictor. In most of the case, majority, I would say more than 80 to 90%, they are using the orifice restrictor. That is because usually the air bearings are small in size or in dimensions, and usually it's very difficult to install the capillary restrictor inside the bearing. Therefore, most of the case they are using the orifice restrictor instead of the capillary restrictor. The second reason is that for the air bearing, it is very difficult to heating up the bearing because the air is constantly exhausting to the atmosphere, so it carries around the heat. Okay? So it never happens the temperature rise in the bearing. So if you don't have a temperature rise in your bearing system, so you don't need to consider using the capillary restrictor. 主要是气体压轴承的话，一般来讲都是用小孔节流器。通常我们会用毛细管节流器，就是温升的问题，造成粘度的温度变化。它其实变化剧烈的话，就要用毛细管。但是因为空气轴承的话，空气会带走热量，所以基本上我们空气轴承不管是主轴还是工作台，基本上都不会有温升的问题。所以一般来讲，它的设计可以用 that's why we consider usually for the air bearing, the instrument equipped with the air bearing, we consider the condition in isothermal. So the temperature rise the air bearing system seldom be happen. Okay. So here is the volumetric flow rate. Okay. Here is an example with air bearing using the slot restrictor. Okay. Here is the formula for that. But normally you can ignore it. Okay. And I say the slot restrictor mainly used in practical applications. 所以狭缝节流器基本上是现有的商品完全没有使用这个设计，所以基本上你可以忽略它，you can ignore this. And here we have some, yeah, these are the special, these are dedicated to the formula for the air bearing, for the slot restrictor is that the flow rate is, okay, and slot restrictor with circular bearing, and this is mass flow rate. Oh, this is circular transparent and for the capillary restrictor for the air bearing. There are some discussions in the beginning of page 46, okay, to discuss some of the parameters here, CT or KP. You should read, I mean, you should read it carefully. Okay, we have also some relationships for the reset pressure, vocabulary restrict. This is for the orifice restrict. Because the orifice restrictor is the turbulent flow regime, so they are divided into different flow types. 小孔节流器通常是用在那个稳流或者是湍流的它的状态，它的流体流动有经过小孔节流器的话是在稳流的状况，它是分成两种，所以你计算的时候会不太一样。So this is the formula for you to estimate the recess pressure. For the air bearing, the theoretical calculation is more complicated. It before it's really causing a problem, but now it's because the power, calculation power of the computer is increasing dramatically. Now it's not a problem. It's before usually when you calculate the recess pressure or mass flow rate for the air bearing, we need to time to wait for the result. Okay, maybe 3 or 4 hours. But now it's really not a problem for the GPU and for the computer. You can get the result in maybe just a couple of minutes. 以前的话都是我们要写那个数值方法去解这个 TDR 轴承的一些方程式，所以要等很久。以前当然老师念博士班的时候大概是2000年左右，所以跑一个次程式都要等4、5个小时才有结果。即使是在工作站上面跑也是这样。但现在同样的程式跑的话，大概就是几分钟5分钟里面大概就有结果。以前的话是要等3、4个小时。那如果是解那个手紧轴承的话，可能各会超过10个小时。We also talk about the virtual reset. Okay. Virtual reset, we will discuss that later. Maybe we talk about the virtual reset later. We really discuss it. Yeah. And maybe I just show you some example. It's in the patent design in page 66. So we'll discuss again in chapter 4 when we show you how to design the pet area. And in the beginning of chapter 4, there is a figure you can look at for the virtual reference. Okay? So for the hydrostatic bearing, because usually we we use the lubricant as the working fluid, and during the normal operation status, the supply pressure is lower than 60 bar, so it's incompressible. So we can design the recess for hydrostatic bearing. But for the air bearing, it's very tricky. With the supply pressure bigger than 5 bar, you are prone to have symmetrical stability for the air. So usually you will avoid to design the reset for your air bearing. And in that case, the load capacity for air bearing is very small. Theoretically, you can have this kind of virtual reset design. Okay, we don't have any reset here, but instead we have multiple inlet ports or supply air supply hole here. It's formed like a normal square, like a recess. Okay, and each outlet of the air supply hole you will have a high recess pressure. So in this case, we said this set up only one example we have here. A kind of design is called the virtual index. Okay, theoretically speaking, is correct, but in practical, it's very difficult. Why? Because every index form you need to install the typing, you need to install the restrictor. So it makes your very complicated and very difficult to maintain and repair. So theoretically it's correct, but practical nobody uses this one. 所以这个是就是理论跟实际是有差距。理论上是讲，空气手诊当然是因为会气水，所以通常我们都设计枪，不设计枪。不设计枪支的话，就变成是我只有入口这一点，枪支压力比较高，其他的都很低。做整个计算起来同样的面积，它的载重就很低，承载力就非常低。那你如果用像这种叫做虚拟枪支的话，你去设计8个入气口，它不是只是一个正方形，就像这个曲形的油枪一样。它每一个入气孔的话，那个 PR 就会很高，所以可以把整个它的 PR 的大小拉起。所以这个是理论上是可以设计成虚拟枪 ，virtual 就是虚拟，但是实物上不行啊。我每一个进气口都要去接管线，每一个进气口都要去接节流器。我只要配管的话，这边只要配1次，这边要配8次，所以实物上没有人去干这种。所以这是理论上讲可以这样。当然，因为这个是研究所的教科书，所以他讲理论的。This is a graduate school textbook. So we need to speak about the theoretical part. I just say there. But in practical, nobody do this. Don't do this. 没有人会去做虚拟。So instead, now they are using the so don't do this virtual prison design for the bearing. So nowadays they are using the porous air bearing. So if you want to increase your load capacity, you need to choose a new type of air bearing called the porous air bearing. 多孔性的气气压轴，那么气气压轴的，它就是整片，它也不用去设计枪，它是整片就是设计多孔性的，所以它就很多孔，整个面都可以有气。但是它的困难就是这个多孔性的材料你要压制在那个面上面，要很均匀的话要很高哈。台湾只有一家厂商会做，但是它也只会做平面。So it's very tricky for the porous air bearing design. Not so many companies can manufacture this product. So far in Taiwan, only one company can do that. So it's difficult to make the porous material homogeneously cover the whole bearing area. 很均值的涂布在上面，它其实是用那个刀节的方式，其实是会做这个也是做陶瓷的厂商，它其实是原来是在英歌 烧那个陶瓷。So if you want to increase your air bearing low capacity or stiffness, you should choose a new type of air bearing. It's called porous air bearing. This kind of bearing, you don't need to design the restrictor because of the porous material behaves like a restrictor. But the difficulty is how you can manufacture the porous material homogeneously cover whole bearing area with equal porosity of the material. That is a very tricky one. 因为我们合作过的一家厂商，那花了大概1亿5千万台币才把它试出那个配方，它其实就跟烧陶土一样，烧陶瓷。So it's very difficult. So only one company in Taiwan they can manufacture this porous air. And the owner of the company told me that he spent more than $5 million just for manufacturing the material. 所以这是另外一种选择了哦。你如果要气低压的工程，又要有大的承载力跟刚性的话，就是用多孔气。In United States, we have three companies manufacture porous air bearing. In Japan, at least you have two companies manufacture. So you should customize the order. You give the dimension of the bearing head and the thickness of the head. Okay. For the journal is the same. You need to give the diameter of the journal and the length of the journal, and also the film thickness during walking. 所以它其实是需要客制化生产。Maybe next hour I'll give you the sample for that. Okay. So forget about the virtual research in this case. So we will come back in chapter 4 to discuss about this. But for the moment, we concentrate when so for the chopped floor, unchopped floor, for unchopped floor here, you have a guarantee, no numerical hammer in this case. And for chopped floor, you will have the risk of numerical instability. Australian company, but it's only a concept. Theoretically, it's correct, but practically, it's difficult to implement. So forget about it. Okay. In reality, we never see this kind of product in commercial product merchandise. Okay, we have some examples how we can estimate the research ratio of the volume flow rate and mass flow rate and low capacity. So in reality, for the supply pressure, I think it's, yeah. So the reset pressure, because the supply pressure usually for the air bearing less than 6 bar. Okay. Commercially, usually the maximum supply pressure for air bearing is 5.5 bar. Most of the cases you will see it's less than 5 bar. Right? It comes to the end of this chapter. So this book is a good book for the air bearing design. Those one. So you can still borrow from the library, not in our university, in Cheng Kung University. I have a copy for this book myself. Yeah. And this, the second one, Tribology Handbook, is also very good handbook for the bearing. So including the air bearing, hydrostatic bearing, and hydrodynamic bearing. Probably you can borrow this one in our library. You know what? It's a British book, textbook, practical textbook. Okay, take a break. This is porous Jonas Berry. It's made of the United States. It costs $1,600. Okay, so you should be careful for this one. So it's porous material, the red one, inside the diameter. Okay. And here we have three truss bearing, truss air bearing. If you look at, you can have a small hole. I believe it's 1.5 millimeter for the diameter of the Olympus diameter. So we have a different groove on this truss bearing. You can have a look. The purpose for the groove, so we have two bearing pad with groove，两个轴承上面有沟槽，一个没有，one without any groove. So the purpose to making groove is to increase the load capacity. 所以挖沟槽就是让它的 PR 的压力变大。那没有沟槽就是 the one without any groove, you only have a supply hole in the center. So, for the next chapter, we will discuss about the power, pumping power, and also for the temperature rise for the hydrostatic bearing. We are pumping the oil in high pressure under very small film gap thickness. So due to the viscosity flow friction, you have you will generate a lot of heat. So in your lubricant. So you will have a temperature rise in your lubricant. Okay. And then we talked about the shape, the bearing at the area. So probably we should so in this chapter we will discuss or we want to estimate the pumping power. So the pumping power is to how you can choose your pressure supply system, the power for your pump. So this pumping power is equal to the supply pressure multiplied by total volume flow rate for your hydrostatic bearing. Okay. This one is the formula to get the pumping power for the air bearing. And we also want to estimate the friction power generated between the small gap film thickness from your hydrostatic bearing. So we can using this formula to estimate for each bearing type how much the friction power will generate if you're running certain rotational speed, okay, under certain film gap thickness, okay. So by assuming the whole friction power will go into the lubricant, then you can estimate the temperature rise for the lubricant. Okay? So this is a pure theoretical estimation. If we don't cool down the lubricant, what is the temperature rise for your system? So usually you will have, I think, 20 to 30 degrees. Most of the case, temperature rise under the operational speed. Okay. So, and this is also the estimation for calculating the friction power you need to have bearing area to calculate the friction. So in this case, you have friction power. You will know what is the pump, what kind of pump you should select for your bearing supply system, and you can you can calculate the total power generated during the operation. Okay, then you know what is the cooling system you should design. If your power supply system should include the cooler design. Okay, so here are the main issues we will discuss in this chapter. And also in this chapter, we will define what is a high speed hydrostatic bearing, what is low speed hydrostatic bearing. Okay, using this the ratio of friction power to the total to the pumping power, then you can define what is a high speed bearing, what is the low speed bearing. So here we have a power ratio definition, the K value. So we're using the K value to define what is the low speed bearing, what is the high speed adjustable bearing. Okay. So here are the main content. So the pumping power declaration, the friction power, power ratio, temperature rise. So we have some assumptions under the calculation of temperature rise. We assume the overall friction power will be go into the lubricant 100% without any radiation or convection to the air. Okay. So this is the worst case scenario. You can estimate the temperature rise for your lubricant. As we know in chapter 1, when you increase your temperature for your lubricant, usually the viscosity will drop when the temperature rises. 所以前面我们第一章讲过，就是当我的温度上升，润滑油的粘度其实会下降。粘度下降的话，就是我的承载力其实都会下降，刚性也会下降。所以为什么我们要去估一下它的温升？因为我们的温度上升以后，上升值多少？For the temperature rise value, you can estimate the viscosity at a certain temperature. 在不同的温度下，它的粘度会变到什么样子？再来的话就是我们，then we have several different design strategies when you design your hydrostatic bearing. It's a bit classical one. So when you look at the research paper in the 60s to 80s, you will have a lot of the research paper concerning the designing of a hydrostatic bearing with a minimum power as a criteria. 所以以前的话，你在早期的文献，就是60年代到80年代的一些研究论文，做了很多一些要怎么的设计，就是在最小功率范围，其实是最小的摩擦功率。Okay. So using the power ratio, we can define low speed bearing, high speed bearing, and we also have a certain speed parameter designed as an indicator to know the some performance of your joint bearing. Okay. So the H is the designer's name, the researcher's name, and then we will have optimization for the planned non-recessed hybrid variant. So as we discussed in the first chapter, for the John Berry, we have recessed variant and non-recessed for planned variant. 有枪式的轴承跟无枪式。Plain 就是平的，没有枪式。Non-recessed 就是没有任何枪式。Usually non-recessed plain variant is for the air variant. So for the hydrostatic variant, usually they are recessed variant. So in this case, we didn't mention whether they are the trust bearing or journal bearing. So now we start to design, start to know, understand some of the theory to design the hydrostatic variant. So we will introduce you some of the design guideline or design rule for the hydrostatic variant. So what is the variant shape, best variant shape, or clearance. Clearance is a terminology, especially for the John Berry. Okay, it's called the clearance is the gap between the shaft and the journal. 所以这个是间隙。Okay, clearance is called it's a special terminology for the John Berry. Okay, and also the pressure ratio. So for different type of the restrictor, usually there will be a different pressure ratio for design your hydrostatic vacuum. Okay. So that you will have a maximum load capacity for minimum power consumption for your hydrostatic vacuum. Okay. This is for the low speed bearing. Okay. And for high speed bearing, here we call the bearing, it's called the hydrostatic bearing or aerostatic bearing. It is important to avoid high temperatures and excessive cavitation of a lubricating film, leading to a range of problems. Okay. Cavitation is a special terminology for the true film bearing. Means in sometimes, especially you have a recessed bearing design, sometimes there is a vacuum place for lack of lubricant in some specific area of the recess that we call it cavitation. Cavitation 叫做那个空隙，其实就是对润滑油来讲的话，就是它其实是那一块就是缺乏润滑油，就只有空气。对，那通常的话是在高转速的话才会有这种情况。高转速而且是有枪式的轴承，它会有 cavitation。So then we also have some design strategy to have our design criteria as a minimum power consumption. It is relative important now for energy saving point of view. Then We will also discuss some of techniques. You need to choose the correct one, choose the right vibration or viscosity for your bearing, okay? And some film techniques, okay, and bearing the area. So there are some design guidelines, rule of thumb to decide what is the viscosity, what is the film technique. Okay. We can talk about it right now. For the viscosity of the hydrostatic bearing, usually decided by the rotational speed, the maximum rotational speed for your hydrostatic bearing. 年度的话，一般是由你的运动速度来决定。我的尽压总是用在高转速、低转速。The higher the viscosity, or the lower the viscosity, the easier it can move. Okay, so 粘度越低的话，它可以运动的速度会越快。So depending on what kind of operational speed for your bearing, so that will decide which kind of viscosity you can choose. So usually by experience, not really by experience. So when you talk about the rotational speed, and another, I would say another reference for you is that you can choose similar product in the market that you are interested in, and then for the viscosity of those products can give you some reference for your design. 所以一般来讲，我们是看那个转速的高低来决定我到底要用多大粘度的。So the viscosity index number, we mentioned that maybe 1 or 2 weeks ago. It's ISO standard. Usually we call it DQ number. So the number can be 2, 5, 10, 15, 32, 46, 60. This is the normal viscosity index we apply the oil hydrostatic bearing. So usually started from the VG number 2, 5, 10, 15, 32, 46, and 64. So for these two, viscosity number higher, you have a higher viscosity. So if you have a small viscosity number, means that you can run it in very high speed. Okay. So for this number two or number five or even number 10, sometimes they are using, mostly they are using for the spindle or a big rotary table with a very large airing head. Airing, okay? Yeah. For the 46 or 64, usually they are flying the skyway system. So depending on your moving speed, you can decide which viscosity is for your lubricant. Okay, of course, we can refer to some of similar products in the market and see what kind of viscosity they are using for the product.所以一般来讲，其实我们会知道不同的主轴转速大概几转，它可能用几号。So just pick one and estimate the friction power. If it's not fulfill your requirement, then you just decrease the subsidy number or increase. Okay? 所以你其实是找一个值来先算算看，如果不行的话，我们再去换。通常的话，大概就是我们大概就会里面找一些商品资料，同样的尺寸的工作台或同样尺寸的组成，它的转速范围是多少，那用什么引擎，基本上就差不多，就是那几种。And for the film thickness, it's also easy to decide. Okay? Usually this was decided by your skill of the assembly worker. So what is the minimum film thickness for your company's assembly guy, assembly worker? They can put together for hydrostatic speaker. 通常的话，其实油墨间隙的部分你是不是太困难决定？你不能选太小，选太小的话，通常你那个组装的功能就会跟你讲很难装，装半个小时都装不进去。当然你也不能选太少。You should pick a right film thickness. If you pick a very small film thickness, it's very difficult for the assembly guy to fit in for your hydrostatic spindle rotating table assembly. It's very difficult to manufacture. But you cannot choose the film thickness too big, then you are lacking of stiffness. 就是你不能选择太小的间隙，太小的油墨间隙就是很难组装，装不进去。然后你选太大的话，就是刚性很小。通常到底多小的话，其实每个工厂不太一样。工厂的组装的功能就跟你讲，这个一条半两条很难装，基本上装个十几分钟才装得进，有些是根本就不行。所以 you can get the feedback from the film thickness from your assembly guy, the manufacturer process for assembly line. Okay, and for the supply pressure and the varying head area, these two will be decided by the load capacity you should carry. For example, for your line cable, you need to hold workpiece with two 20 tons, and then you have an extra cutting force. So these two plus together is your maximum loading for your bearing head. Okay, for your bearing. So you have a maximum workpiece weight plus maximum. So this is the load capacity you need to have. And you have for example, you have a four bearing pan in your slide table. 在你的工作台如果有4个轴承，那这个就是1个轴承的面积乘以4，就要等于你的工作台的总重量。工作台的封建重量其实还有轻重。So slide table weight plus the maximum workpiece weight and plus the maximum cutting force. That will give you the overall load capacity. 所以其实没有太困难你有最大的轴向切削力，有最大的封建重量，工作台本身的自重。那你有4个轴承去承担，那你就知道一个轴承要承多大。So, and you can give estimation for your bearing head, and also give you some range for your reset pressure. 所以总重量知道，我有几个一定要轴承要去承，那我就知道我的 PR 要多少。PR 知道我就知道我的 PS。So once you know your reset pressure, then you know your what kind of a restrictor you choose, and then you know the right pressure. So in this chapter, we'll give you the what is the I would say what is the proper choose for your pressure ratio. For the second chapter, we discuss about the pressure ratio, recess pressure, divided by supply pressure. Okay. For different restrictor, you have some range to choose your pressure ratio. 不同的节流器，它会选不同的压力的范围。所以一旦我们大概估出它大概的油箱压力，其实我们知道我们选用的节流器，就会知道供油压力要是多少。那供油压力知道我们前面的这些都可以算出来。Once you know the supply pressure, then you can estimate the pumping power. Okay. Once you decided your bearing area, then you can estimate the friction power. Okay. So it's not so difficult, but some of them you should design use with the leg beforehand. Okay. But you can always estimate the performance. If it is not fulfilled, you can always change it and take you in again. Okay. Is there any problem or any questions for the lecture? Okay. We have, still 5 minutes or 4 minutes. So now we start to design the bearing. Okay. Any questions for today's lecture? Okay.